morning, good evening, depending on when you are. My name is Rashid Zeglash, and I'm your moderator for today's session. We are thrilled to host Yasar Mehmood, a teaching fellow from the IT University of the Punjab in Pakistan, for this highly practical workshop on brain tumor segmentation with units using the BraTS Dataset. Before we dive into the technical details, a few quick housekeeping items for the session. The format will be, I will be playing a recorded tutorial from Yasar that cover everything from data handling to the 3D unit implementation. Concerning the question, please post your question in the chat throughout the session. We will be having a dedicated Q&A at the end to address them. Concerning the resources, we have all the code available on our website now, in the RISE-MICCAI tutorial website. So we encourage you to share the repository link with your colleagues or any of your peers that might find benefit from this work. Concerning the recording, if you want to revisit any part of this workshop, the recording will be available on the MICCAI Society YouTube channel shortly after we finish. So let's get started with the tutorial.
Hello everyone and welcome to this tutorial on brain tumor segmentation. My name is Yasar Mehmood and I'm a teaching fellow at the Information Technology University of the Punjab. Today we are going to bridge the gap between medical imaging and deep learning by building a pipeline to segment gliomas using the unit architecture and the BraTS dataset. Whether you are a student or a researcher, this session is designed to give you a hands-on end-to-end experience in medical AI. So before we dive into the code, let's take a moment to look at the big picture. In clinical practice, analyzing brain tumor is incredibly challenging. They don't have a standard shape, they are fuzzy and irregular. Traditionally, radiologists have to manually trace these boundaries slice by slice. Not only is this exhausting and slow, but it's also subjective. Two experts might look at the same scan and disagree on the tumor's edge. By using AI for volumetric segmentation, we provide doctors with objective and consistent measurements that are vital for planning safe surgeries and monitoring how a tumor responds to treatment over time. So our roadmap for today follows a professional medical AI pipeline. We'll start by exploring the multi-modal nature of MRI scans, looking at different sequences like T1, T2, and FAIR. Then we'll move into data engineering, converting raw medical files into PyTorch tensors. And the heart of this tutorial will be building the unit architecture from scratch and comparing 2D versus 3D approaches. Finally, we'll evaluate our model using the DICE score, which is the industry standard for measuring segmentation overlap. And the target audience for this tutorial is everyone who is excited about the intersection of healthcare and AI. So if you have done basic image classification but want to move into the more complex world of 3D medical volumes, or if you are a healthcare professional curious about how these diagnostic tools actually work under the hood, you are in the right place. To get the most out of this tutorial, you should have a basic starter kit of knowledge. I assume you're comfortable with Python and the basics of PyTorch like creating tensors and datasets. You should also understand the core concepts of CNNs, things like convolutions and pooling. Most importantly, remember that today we are not just classifying an entire image, we are performing pixel-wise or voxel-wise classification, where we assign a label to every single point in the 3D volume or a 2D slice. And on the domain side, you don't need to be a radiologist, but you should understand that an MRI provides a 3D volume rather than a flat photo. And now a very important note on resources. One of the core values of this tutorial is accessibility. This pipeline is specifically optimized to run on the Google Colab free tier. So you don't need a pro account. The free T4 GPU is enough. However, because medical data is large, please ensure to have about 50 GB of free space on your Google Drive to store the dataset and your model checkpoints. And if you have that ready, we are good to go. That we have the overhead view, let's dive into the core concepts. In standard AI, we often talk about classification. Is there a tumor or not? But for a surgeon, this is not enough. We need to know exactly where the tumor is. Segmentation is the process of pixel-wise or voxel-wise labeling. In the BraTS challenge, we go even deeper by identifying 3 distinct subregions of a tumor. We look for the necrotic core and non-enhancing tumor core, the peritumoral edema, which is the swelling around the tumor, and the enhancing tumor, which is the most active part of the lesion. This level of detail is what makes our AI clinically useful. Okay, why do we need this pixel perfect accuracy? Think of these segmentation maps as a GPS for a neurosurgeon. It allows them to maximize the removal of the tumor while carefully avoiding healthy brain tissue. It also allows oncologists to aim radiation beams with precision, and it gives us an objective way to calculate tumor volume. This is how we move from a doctor's best guess to data-driven medicine. You might wonder, why are we using the 2019 version of the BraTS dataset instead of the latest 2024 or 2025 releases? The reason is practical accessibility. Modern BraTS version now contain thousands of high-resolution scans, which are excellent for state-of-the-art research, but can easily overwhelm the storage and processing limits of a standard Google Colab environment. The 2019 cohort is much more manageable, featuring only 335 expert label scans. We still get to work with all 4 standard MRI sequences, which are T1, T1CE, T2, and FAIR, giving you the exact same multi-model experience. Finally, we come to the engine of our project, the UNet architecture. Introduced in 2015, it remains the gold standard for medical segmentation. It uses a symmetric U shape on the left. The encoder captures what is in the image by compressing the data. On the right, the decoder recovers where these features are located by expanding it back to the original size. But the real secret sauce is the skip connections. These act as shortcuts, carrying fine-grained spatial details from the encoder directly to the decoder, ensuring that our tumor boundaries remain sharp and anatomically accurate. Okay, before we start working on the hands-on implementation, let's import the necessary libraries. And you should run this code cell to mount the Google Drive. And this is the path of tutorial data where we will save our dataset and model checkpoints. And within this folder, so when you will extract the downloaded BraTS 2019 within this folder, then it will automatically create this folder that will contain the complete BraTS 2019 dataset. So this will be our dataset path, right? And I am not explaining how to download the BraTS 2019 dataset directly from Kaggle to your Google Colab, right? But I have provided the detailed instructions to do so, so you can do it yourself. And alternatively, you can manually download the BraTS 2019 dataset from this link, right? This URL, and then you should extract it and make sure that these dataset paths are consistent, right? I mean, they are correctly set, or the dataset actually exists within this path, right? And finally, you should run this code cell just to make sure that we are able to use the GPUs during hands-on implementation. And an important thing before you start executing any code cell, you should make sure that your runtime is selected to this T4 GPU, right? So the T4 GPU is enough for this tutorial notebook to run without any problem, right? And we will be able to train unit 2D and unit 3D without any issues using this T4 GPU that is available as part of Google Colab free tier, right? So if it is not already selected, then you should select it and click save here. So so that means you will be able to use this T4 GPU right, for this tutorial. Okay, let us now start hands-on code implementation. Before we dive into the exploratory data analysis, we need to address a silent challenge in deep learning, that is stochasticity or randomness. By default, every time you run a neural network, the initial weights and the way your data is shuffled are slightly different. This means if you get a great result today, you might not be able to replicate it tomorrow. We need to make it easy for others to verify the results of our experiments. So take a look at the set seed function on the screen. We are doing three things here. First, we log the basic Python and NumPy generators. These statements are doing this job. Then we use manual seed for CPU and current GPU and include manual seed all as a best practice to ensure consistency even if we were working with multiple GPUs. These highlighted statements are doing this job. And finally, we enable deterministic mode. This forces the NVIDIA hardware to use the exact same mathematical algorithms every time, prioritizing reproducibility over raw speed. So these are the statements doing this job. So let us run these code cells. By running setSeed 42, we ensure that our data splits and our models starting points are exactly the same every time we run this notebook. Now that our environment is ready, let us look at how the data is organized. For this tutorial, we are using the BraTS 2019 dataset hosted on Kaggle by Yasar. The dataset is divided into two primary clinical categories: HGG or high-grade gliomas, which are more aggressive, and LGG or low-grade gliomas. Within each of these, each patient has their own dedicated folder containing 5 critical Nifty files. As you can see in the directory tree, we have the 4 standard MRI sequences: FLAIR, T1, T1CE, and T2, alongside the set file, which is our ground truth segmentation mask. So a quick technical warning here. Different mirrors of this dataset often have varying levels of folder nesting. To avoid path errors, please ensure that you are using the specific Kaggle version of Yasar. This ensures our code can locate and load the scans seamlessly. So let us perform sanity check on our data. In medical imaging pipelines, a single missing modality or a corrupted mask can cause your model to fail silently or crash hours into a training run. This function count dataset statistics, traverses our HGG and LGG folders to verify that every patient has a complete set of files. We are specifically looking for the 4 MRI modalities and the ground truth segmentation mask for every single case or patient. By running this, we confirm that our total number of patients are as expected and ensure that our data is balanced and complete. Let us run these cells. It will take some time because it will traverse all the directories, the entire directory structure of our dataset. Okay, now let's print the dataset statistics. So you see for HGG patients, for HGG class or high grade gliomas, we have total 259 patients, and each patient has these 4 files or sequences. Okay, so the total number of T1, T1CE, T2 and FLAIR sequences are 259. And then again for HGG patient we have 259 segmentation masks. Similarly for LGG we have 76 patients and 76 files for each of these sequences and the segmentation masks. So it means our dataset is correctly downloaded and unzipped. Now let's move to the most exciting part, that is actually seeing the brain. Since we have two types of tumors, the fast growing HGG and the slower growing LGG, we want to compare them side by side. First, use the random patient path function to grab one random person from each group. Let us run this code cell. Then our load BraTS case helper pulls the actual 3D data into our code. Because raw MRI data has voxel values with a very wide range, displaying them as is does not produce clear images. We use normalize to uint 8 to squash these values into a standard 0 to 255 range. This makes the images much clearer for our eyes to see on a screen. Let's call these methods to choose one patient each from HGG and LGG folders and load their T2 modality. I'm loading here T2 modality, but please feel free to load any other modality. Finally, think of a 3D brain scan like a loaf of bread. So if we only look at the first slice, we might miss the tumor entirely. So to get the full picture, we programmatically pick 3 slices, one near the front, one in the middle, and one towards the back at the 25%, 50%, and 75% marks. This ensures we can see exactly how the tumor looks across the entire volume. So let us run this code cell and see the results. So you see we have displayed HGG slice 38 and LGG slice 38. Slice number 77 for the chosen randomly chosen HGG patient, and this is for the LGG patient, and similarly these are slice number 160. Now that we can see the brain, we need to understand the segmentation masks. In a normal photo, a pixel represents a color, but in medical AI, a pixel in a mask represents a tissue type. Think of the mask as a digital map that an expert radiologist has manually painted. We use the np.unique function to find the unique numbers in this data, or uh, the number of classes in the segmentation masks. You will notice the numbers 0, 1, 2, and 4. These are our map legend. 0 is the background, just healthy brain or empty space. 1 is the necrotic core, the part of the tumor that is no longer active. So basically it may be necrotic core or non-enhancing tumor. Label 2 represents the edema. This is the swelling or fluid around the tumor. And class number 4 is the enhancing tumor, the most active growing part that lights up on the screen. Okay, this is another exciting part of our exploration, the overlay. Instead of looking at the MRI scan alone, we now superimpose the expert annotated tumor regions directly on top of it. This allows us to visually verify where the tumor structures are located in the brain. In the code, we use a trick called masked, where this tells Python to ignore the zeros, the healthy parts, so they stay transparent and only draw colors where a tumor actually exists. Now let's run it. You see the results. By using a 50% transparency or alpha here, we can feel the anatomy underneath the colors. So this allows us to visually inspect how different tumor subregions, such as the core and the surrounding edema, are distributed within the brain. This kind of visualization is primarily a sanity check. It helps us confirm that segmentation masks are correctly aligned with the MRI scans before we move on to the training of our model. Static images are helpful, but remember that an MRI is a 3D volume. Think of it as traveling through the brain from the base of the skull all the way to the top of the head. In this section, we have created an interactive slider to make that possible. Our show slices function sets up a side-by-side view. On the left, you will see the original grayscale MRI scans, and on the right, we apply our masked overlay technique. Now let us run these cells. This is the interactive slider for the randomly chosen HGG patient. So as you move the slider, Pay attention how the tumor regions appear and disappear across different slices. The underlying MRI remains visible in grayscale, while the tumor regions are highlighted in color. Let us run this or view this slider for the random LGG patient. So go ahead and play with the slider to explore how the tumor appears across different slices in the volume. To ensure that our tutorial runs smoothly within Google Colab's memory limit, we'll work with a subset of the BraTS 2019 dataset that has a total of 335 patients. In the code, we use a simple form of stratified sampling by selecting a fraction from each class. So this means we take a proportional amount, 10% from both the HGG and LGG categories, helping our mini dataset maintain a similar mix of tumor types as the original dataset. And this collect patient data function, it handles this by selecting 32 patients in total, out of which 25 are HGG and 7 are LGG. So if you have a more powerful GPU or a pro subscription, please feel free to increase this subset fraction later. Let us run these cells. So for now, this is a practical size to demonstrate the unit's capabilities without overwhelming the environment. Now we need to divide our 32 patients into groups for training and evaluation. It is important to clarify the BraTS dataset structure. While the official validation set exists, its segmentation masks are not available to the public. Furthermore, the official test set is not publicly available at all, neither the scans nor the labels. Therefore, for this tutorial, we must create our internal splits using the official training data. We have chosen a 75, 12.5 and 12.5 percentages split. This gives us 24 patients to train the model, 4 to tune it during validation, and a final 4 for a held out evaluation within our subset. So in this code, we use a two-step process. With the trained test split function, we use the stratify parameter both times. Here it is. We use the stratify parameters both times to ensure that our LGG and HGG patients are distributed proportionally across all three sets. By keeping our random state 42, we ensure this splits remains consistent every time we run the notebook. So let us run this cell. And finally, we run a verification check to confirm that each set maintains a similar proportion of both tumor grades. Remember, because these are internal subsets, our results are for learning purposes and should not be reported as official BraTS 2019 leaderboard scores. So we can see these three sets: training, validation, and held out. and the proportion of HGG versus LGG in each of these sets. Now to get our data ready for the unit model, we need these three utility methods. First, load Nifty is a simple wrapper to pull the raw numerical data out of the Nifty files. Let us run it. Next, we have normalized volume. Unlike the 0 to 255 scaling we used earlier for visualization, this performs Z-score normalization. It shifts our data so it has a mean of 0 and a standard deviation of 1. This is an important step because it standardizes the input data, which typically helps stabilize and improve training. Let us run this cell. Finally, we have remap labels. As we saw earlier, the official BraTS labels are 0, 1, 2, and 4. Most classification losses in PyTorch, such as cross entropy, expects labels to be consecutive integers starting from 0. So we simply change all 4s to 3s. So this gives us a clean consecutive set of classes 0, 1, 2, and 3, which aligns with the expected format of the model's output. Now we'll set up our data for the 2D unit. Even though a brain scan is 3D, we're going to train our models slice by slice. In the code, you will see the BraTS 2019 slice dataset class. This one. Its main job is to take the 4 MRI modalities, T1, T1CE, T2, and FAIR, and stack them together. This creates a 4-channel input. Think of this like a standard colored photo that has red, green, and blue channels. But here our channels are different medical views that help the AI see different parts of the tumor. And one practical detail, medical volumes are large. If we loaded a new 3D file for every single 2D slice, our code would be incredibly slow. To fix this, we use a simple caching trick in the getItem method. It only loads a new volume when it moves to a different patient. So let's run this class. Finally, we create our data loaders. We are using a small batch size of 4. While this might seem low, it's a practical choice to ensure we don't run out of memory on the Google Colab free tier. So these are the data loaders: train, validation, and test. So after setting these up, we run a quick sanity check. We pull one batch of data and check it. We expect to see 4 channels for the image and a single 2D mask per slice. Let's see. So here you can see the shape of the input data, 4 channels. 4 is the batch size and 4 channels for each slice. and its spatial dimensions are 240 by 240, and this is the dimensions of the segmentation mask. 4 is the batch size, and 240 by 240 is the spatial dimension of the slice. Now let's look at the implementation of our 2D unit. We're following the modernized symmetric design discussed earlier. For a visual reference of how the layers of a unit connect, please refer back to the unit diagram in the introduction section. We begin by defining the double conf block. And this is the fundamental building block of the network. Here it is. It consists of two convolutional layers, each followed by batch normalization and ReLU activation. We use a kernel size of 3 with padding of 1 to preserve the spatial dimensions of the feature maps, while batch normalization helps stabilize the training. The 2D unit model, the class name is unit 2D. It is organized into three main components. First is the encoder or contracting path, which captures context by progressively downsampling feature maps using max pooling. So this is the definition of the encoder block. The bottleneck, which represents, this is the bottleneck, which represents the deepest level of the network and captures high level features. So this is the bottleneck. And the decoder or expanding path, which restores spatial resolution using transposed convolutions for upsampling. So this is how we define the decoder part, and this is the output. So in the decoder, here this is the forward method, and you see in the decoder torch.cat method, this operations implement the skip connections where feature maps from the encoder are concatenated with the upsampled features at the same level. And this allows the model to combine high-level contextual information with fine-grained spatial details, which is essential very effective for accurate segmentation. And finally, the output layer uses a one-by-one convolution to map the features to the desired number of classes, and in this case 4 classes, 1 background class and 3 tumor subregions. Let us run this code cell and let us create our unit 2D model. We have 4 input channel and 4 classes, and we will print this model as well. So you can see the model has been printed in the output. Now let's talk about how we guide our model's learning. In brain tumor segmentation, we face a major challenge, that is class imbalance. The background occupies most of the image while the tumor regions are relatively small, and can be easily missed by the model. To address this, we use a hybrid DICE plus cross entropy loss, often referred to as a DICE. This combines two complementary objectives. First, cross entropy, which provides stable pixel-wise supervision and helps the model distinguish between different classes. And then DICE loss, that focuses on the overlap between predicted and ground truth regions, making it especially useful for learning small tumor structures. And in the implementation, the DICE loss first computes the standard cross entropy loss using the raw logits. Here it is. Here it is. Then the logits are converted into probabilities using the softmax function for the DICE computation. For the DICE term, we compute the overlap between predicted probabilities and ground truth for each class, and then average across all classes. So this ensures that all classes, including small tumor regions, contribute to the learning process. So finally, we combine the two losses using equal weighting, giving us a balanced objective that is widely used in medical image segmentation for its stability and effectiveness. Okay, with our model and loss function ready, we now define our hyperparameters. These are the tuning knobs that control how the model learns. So we are using the ADAM-W optimizer with the learning rate of 10 to the power minus 4. ADAM-W is widely used in modern deep learning because it handles weight decay more effectively than the standard ADAM optimizer, helping improve training stability and generalization. Okay. So for this tutorial, we set the number of epochs to 1. While a practical model would require many more epochs to achieve a strong performance, this allows us to quickly verify that the full training pipeline runs correctly within limited time and computational resources. Therefore, we will train this model only for one epoch. Before training, we perform a sanity check. We take a single batch of 4-channel MRI slices and pass it through the model and see its dimensions. So from the printed shapes, we can see that the input has 4 channels for 4 sequences because we had stacked them together, and the model produces an output with 4 channels, 1 for each class, a background plus 3 tumor subregions. And this confirms that our data and model dimensions are consistent and the forward pass is working as expected. Okay, moving on to the training loop. Let's look at the train unit function, which is the heart of our training process. The training loop is divided into two distinct phases. In the training phase, we set the model to train mode, which enables the training specific behavior such as batch normalization updates. Here it is. So for every batch of slices, we first reset the gradients using optimizer.zeroGrad, then perform a forward pass, calculate the dice CE loss and use loss.backward to compute the gradients. The optimizer then updates the model's weights to minimize that loss. You see, here is the code that is performing these steps. And in the validation phase, we switch the model to eval mode and use torch.noGrade context. This tells PyTorch not to calculate gradients. This is the eval mode. So you will notice a save best model section. We track the validation loss and save the model's state dict whenever the performance improves. This ensures that even if our model starts to overfit later on, we always keep the best version. And remember that during the validation, we evaluate the model on data that it has not been trained on directly. And a practical tip for larger projects, while we are only saving the best model here, in a full-scale research setup, it is common to save training checkpoints at regular intervals at one extreme after every epoch. So these checkpoints typically include not just the model weights, but also any additional training state needed to resume training seamlessly, such as optimizer state, learning rates, scheduler, current epoch, and other tracking variables. So this ensures that training can continue reliably even after interruptions, such as a collapse session, timeout, or a system restart. So let us run this code cell and let us run this cell to start the training. You will see the progress bar for training, and once the training phase is complete, you will see the progress bar for validation, giving us a real-time look at how our unit is evolving. So it will take around 40 minutes to complete the training of one epoch. So I'll resume the lecture once the training is complete. Okay, so you can see that our training has completed, and Now it's the time to see how our trained model actually performs. One important clarification is that our code does not use the best model that was saved during the training, but since we have just trained the model for one epoch, so the best model and the most recent model, they are both the same. And in medical imaging, we don't usually rely on simple accuracy because brain tumor are often small compared to the whole brain, and it is possible that a model could achieve an accuracy of 99% by predicting everything as a background. Instead, we use the DICE score. So you can think of DICE score as the overlap metric. So basically, we are asking the model, how well does your predicted tumor area overlap with the ground truth provided by the radiologists? So here is our multi-class DICE method that calculates the per class DICE score excluding the background class. So during training, we used soft DICE with probabilities so that the model could learn. For evaluation, we first convert the model outputs into discrete class predictions using argmax and then pass those predictions into this function. Here, note the denominator equal to 0 check. So it means that if a tumor class isn't present in both the prediction and the ground truth for a slice, the DICE score is undefined for that slice, and we return NaN and exclude it from averaging. Our evaluation loop runs in model.eval and no-grad mode. The most important part here is the averaging logic. Here it is. So we filter out the NaN values we just discussed in this statement. And this ensures we only average scores for slices where the specific tumor region is present. Otherwise, the many empty slices could bias the final score and give a misleading estimate of performance. And finally, we map our numerical labels to clinical terms like necrotic core, edema, and enhancing tumor. Let us run the cell and see our model's performance. So it will take some time. Okay, so you can see the results. Typically, edema gets a higher score because it is the majority class, but in this case, by chance, enhancing tumor has got slightly better score than edema. Okay, so far we evaluated our model slice by slice, but in practice, especially in challenges like BraTS, performance is measured at the patient level using full 3D volumes. Even though our model is 2D, we can reconstruct a 3D prediction by stacking the slice-wise outputs. So the DICE score is computed in the same way as before, but now over the entire 3D volume. comparing predicted and ground truth voxels for each class. So in the code, we load each patient's MRI volumes, run the model slice by slice, and then stack the predictions to form a full 3D segmentation. We then compute dice per class at the volume level and average across patients, ignoring undefined cases. Let us run these cells and see the volume-wise results. Okay, so these are the volume-wise results. One important limitation to note here is that since the model processes slices independently, the segmentation may appear inconsistent across slices, and this is one of the key motivations for using the 3D models. Okay, we have seen the numbers. Now let's look at what the model is actually doing. Visualizing the predictions often reveals details that metrics alone can miss. So here we are just randomly picking one patient from the test set. The idea is not to do a full analysis, but to demonstrate the workflow end to end from data loading to prediction to visualization. We load all four MRI modalities, T1, T1CE, T2, and FLAIR, and apply the same normalization we used during the training. We also load the ground truth segmentation and remap the labels so everything is consistent. Now, even though we are working with 3D data, the model is 2D, so we process the volume slice by slice, run inference, and then stack the predictions back together to form a full 3D volume. Now, instead of showing random slices, we first find slices that actually contain tumor. Then we randomly pick a few from those so that our visualization is meaningful. In side-by-side comparison or visualization, we show three panels: the input MRI slice of FLAIR sequence, the ground truth in the middle, and the model prediction on the right side. So you see, this is slice number 117, this is the ground truth, and this is the model prediction. This is slice number 100, ground truth and model prediction, and this is for slice number 42. And we also overlay the prediction on top of the MRI slices. So this is useful because it shows how well the segmentation aligns with the underlying anatomy, especially around tumor around boundaries. So This is slice number 117, slice 100, and slice 42. Okay, so far we have been working with a 2D unit which processes one slice at a time. That's sufficient, but it ignores context along the z-axis, which is actually very important in medical images. So why should we move to 3D? So in MRI, structures are inherently 3D. So a tumor does not exist in isolation within a single slice. It spans across multiple slices. So with 2D models, you often see inconsistent predictions across slices, jagged or discontinuous segmentation. A 3D unit helps address this by learning spatial context in all three dimensions. So the core challenge here is memory versus context. A full BraTS volume is 240 by 240 by 155. And since we are stacking four modalities together, so it will have 4 channels. And feeding this directly into a 3D network is very memory intensive and typically won't fit on standard or may cause the session on Google Colab free tier to crash. So instead we use a patch based strategy. So instead of using the full volume, we use patches, and during training we randomly crop 3D patches of size 64 by 64 by 64. So this is the dataset class for unit 3D, and you see here we have random spatial crop, and it will be used during the training, right? It keeps memory manageable, and it introduces variability across epochs, effectively acting as data augmentation. So for the exact patient, for the same patient, in one epoch you will get a different patch from a different location, and in the next epoch you will likely get a patch from a different location. So it acts as data augmentation. Okay, but during validation and testing we use center crop. We crop the patch from the center, and this is done to ensure consistency and reproducibility. And so we still keep the same 4 modalities, right? But now the input shape becomes C for the channel dimension for 4 modalities. D is the depth, which is 155. H is the height, and W is the width. So C, D, H, W should be the dimension. So you see here that we have stacked all the 4 sequences, and here we are changing the dimension into this form, right? And similarly for the segmentation mask. So you see, otherwise this dataset class is very similar to the dataset class for unit 2D, and so let us run it. So So we use a patch size of 64 by 64 by 64. I mean, you may use a larger patch size or a smaller patch size like 32 by 32 by 32. It depends upon you or your resources, right? So because 3D data is heavier, so we reduce the batch size. So here we are using a batch size for 2. And let us run this code cell. And finally, for sanity check, let's verify that the input shapes and mask shapes are as expected. So you see 2, 4, 64, 64, 64, where 2 is the batch size, 4 is the channel dimension for 4 sequences, and 64 by 64 by 64 is the patch size, is the, right? So next, let us see the implementation of units 3D, right? So it is quite similar to unit 2D, but the double conv block is now implemented using 3D convolutions along with batch normalization and ReLU. Right, and this allows the model to learn spatial features not just within a slice but also across slices along the depth dimension. The overall structure remains the same. We have an encoder part, a bottleneck, and a decoder block. But the main difference is that we are using conv3D and using maxpol 3D for downsampling and conv transpose 3D for upsampling. So another important difference is that it's relatively lightweight compared to the unit 2D. We use fewer levels and a smaller number of filters. So this is because 3D models are significantly more memory intensive, and we want this tutorial to run on Google Colab's free tier. Right. So here you can see skip connections that concatenate the encoder features to the decoder features at the corresponding level. So let's create our 3D model. Input channels 4 and number of classes 4. And this is our base filters. Just like 2D unit, we are using the die CE loss, but of course this is the adapted version, adapted for 3D data, right? But the logic is pretty much the same, right? So the inputs are now volumetric. So instead of HW, we are working with DHW. D is for depth dimension, and cross entropy is computed exactly the same way. For the dice term, we apply softmax, convert targets to one hot, and compute overlap, but now across the entire volume. So the real difference is that dice is computed over voxels instead of pixels, while the overall formulation remains unchanged. Okay, so these are the hyperparameter settings for unit 3D. We are using a learning rate of 10 to the power -4 ADAMW optimizer, and you might have noticed here that we are training the model for 15 epochs, right? So the reason is that even though the 3D model is heavier, it takes more time per sample. We use a patch-based approach, so we only process one patch per patient per epoch. In contrast, the 2D model processes all slices, leading to many more data points and many more iterations per epoch. So that is why one epoch of the 2D unit, it took around 40 minutes when I trained it. So in this setup, the 3D training is actually faster per epoch, and I have explained the reason for that. So it allows us to train for more epochs. Let us set these hyperparameters. And finally, the sanity check. Just to verify that input, output, and mask shapes, and also check the GPU memory usage. Now the training loop for unit 3D is almost identical to the unit 2D's training loop. The main difference is obviously that we now process 3D patches instead of 2D slices with inputs of shape, batch size 4 DHW. We compute the dice plus cross entropy loss, perform back propagation, and update the model using ADAMW. After each epoch, we run validation and save the best model based on validation loss. So overall, the pipeline stays the same. The key change is learning from 3D context. So let us start the training. And as I told you earlier, it trains much faster because we have very few data points, and I hope that it will on average take less than a minute per epoch. Okay, you can see that 15 epochs have completed. The unit 3D is now trained. Now we perform evaluation in a patch-wise manner rather than on a full volume, since the model operates on 3D patches due to memory constraints. And each samples from the data loader corresponds to a 3D patch, and we compute the dice score per class over all voxels in that patch. Right? This is quite similar to the slice-wise evaluation of unit 2D. But the limitation of this approach is that it does not capture global consistency across the full volume, which is why full volume evaluation is preferred in benchmark settings. So this is the, let us see the results of patch-wise evaluation. So you see the best results are for edema class, which is the majority class. Now for full volume evaluation, we use a sliding in window inference strategy to to reconstruct predictions over the entire 3D scan. So instead of processing the whole volume at once, we move a fixed size 3D patch across the volume with some overlap. So for each patch, the model predicts class probability. Let us see the code. Since patches overlap, each voxel may receive multiple predictions, and we accumulate these and take their average to obtain the final probability at each voxel. So after aggregating all patches, we take the argmax to produce the final segmentation for the full volume. Here. We then compute dice score per class over the entire 3D volume, excluding cases where a class is absent, and finally average these scores across all patients. Okay, so these are the volume-wise results, and again you can see edema has got good score. Okay, to visualize the unit 3D results, we start by randomly selecting a patient from the test set and loading all 4 modalities of this patient along with the ground truth segmentation. We then run sliding window inference to obtain a full volume prediction, ensuring that we are evaluating the entire scan rather than just a single patch. Next, we identify slices that contain a higher proportion of tumor pixels. This helps us focus on the most informative regions for visualization. And from these, we randomly select a few representative slices to display. Finally, we visualize each selected slice in 3 orthogonal views that are axial, coronal, and sagittal, showing the flare image alongside the ground truth and the model's prediction. So this is the axial view, this is the coronal, and this is the sagittal view. This is ground truth, and this is prediction. Now, to better interpret the model's prediction, we visualize segmentation overlays on top of the FLAIR MRI sequence. For each selected slice, we display the grayscale FLAIR image as the background and then overlay the segmentation mask. The same visualization is shown side by side for the ground truth and model's prediction, making it easy to compare their spatial alignment. So this is the ground truth overlay for slice number 87, and this is 3D prediction overlay. You see, in the predicted, we see a lot of green color that corresponds to edema, since it is a majority class. So the model is incentivized to predict edema, and that is why we see a lot of greens on many places. It is predicted on many voxels. So that's it. That is the end of our pipeline from brain tumor segmentation. We started from exploratory data analysis. Then we selected a subset of data set so that we could train the models within our while using the computational resources available through the Google Colab free tier. Then we trained Unit 2D, evaluated it, and visualized its results, and we repeated the same process for Unit 3D. Let us now have a brief discussion or mention of the challenges and limitations of this tutorial. So first of all is that we have used a very small subset of data because of the scarcity of computational resources. But if you have enough resources, you should use the full data set. Secondly, for training on high performance computing cluster, you would of course transition this notebook to a modular Python scripts, right? Now, this is oftentimes challenging for researchers, especially in the resource constrained settings, to gain access to these high-end resources. So you should look for academic collaborations or mentorship programs like the RISE-MICCAI mentorship programs, not only to get a mentorship, but you may also get access to the computational resources, right? And then you should use robust checkpointing. You should save checkpoints with all the tracking variables, so that you may resume your training if it is interrupted abruptly. And please feel free to consider increasing the model width, depth, and input resolution if you have high-end resources. So the hyperparameters we used here are reasonable starting points, but feel free to change them and employ a systematic search to find the optimal hyperparameters for state-of-the-art results. And we have downloaded the BraTS dataset from a Kaggle repository, but if you want to publish your results or you want to participate in a challenge, you should always use official data sources. Now play with this notebook and get comfortable with unit architecture. And once you are proficient in using this architecture, your next step should be the NN unit framework. It's a self-configuring configuring framework, and I mean, it automatically selects hyperparameters or settings for you for your data set, right? And so you quickly achieve good results, and you are free to focus on your research goals rather than wasting time on low-level configuration. Now, UNet is based on convolutional neural networks, so it is a type of CNN, right? But you should explore transformer-based variants like Unit R or Swin Unit R. And finally, you should definitely explore the foundation models for a medical image segmentation like MedSam2. So they allow us to provide visual prompts for better segmentation. Finally, thank you all for taking the time to go through this brain tumor segmentation tutorial with me. I hope it gives you a solid foundation for working with 3D medical data and deep learning. I wish you the very best in your journey, and I hope your work leads to meaningful and impactful contributions in medical imaging and AI. Good luck, and thank you very much.
Okay. So it was very nice session. Now we'll be heading to the questions.
So I have answered most of the questions that were asked during the session, but a couple of questions. Will I receive a certificate? I think Rashid, could you please answer this?
Yeah, of course. I will be sending you.
Okay, so you will receive certificate for this session. So I think okay, and okay, so
That will be
another.
I will be maybe reading the question and then you can answer all the questions. Okay?
Yeah, sure.
If
Please go
you
ahead.
let me see whether so let's start with like so the first one. What is the difference between brain tumor classification and segmentation in medical imaging? So I guess you already answered, but could you like please give us more detail about like question?
I think I've answered it. So, in classification, we predict a class for the entire image or the volume, right? But in segmentation, we predict the class of each pixel or voxel. So, in segmentation, we are able to predict the exact location of the tumor or the background, right? So this is the main difference between segmentation and classification.
Okay, perfect. So let's go through the questions. So from Maya, I would like to know if we have access to the notebook collab. Yeah, of course, we have access. There's like a link. You will have like a link in the YouTube description, and also it is available on our website, which is the RISE-MICCAI website. So I
Rashid,
will
could
be
you
sharing
please
this.
repeat? Could you please repeat?
Yeah, the question or the answer?
The question,
Yeah,
please.
the question is, I would like to know if we have access to the notebook in collab.
Yes, of course. I mean, it's. I think you guys have already uploaded it, right? So
Yeah, that's why I answered your place.
yeah,
Sorry.
yeah. One.
Perfect. Um, let's go for the other one. It is possible to get the notebook to follow along. I am Youssef Bien, the presentation So the presentation, so unable to follow the presentation. Yeah, you are already answered. Yeah, of course. You will have from Maya, where can you share the URL with me, please? Yeah, you should. Perfect. From Amer is HTG and LTG classification of brain tumors, same as stage for some cancer like stage 1, etc.
I honestly, I mean, I'd rather leave it to an oncologist to answer this question.
Okay, okay, yeah, perfect. Okay. Um, from Amer, are slides done or made by dividing the full complete scan into many images, or is it processing? It's a bit confusing like this.
Yeah, so it's part of the acquisition process that, I mean, during the acquisition process, the scanner uh, gives us the 2D slices that are stacked together to form a 3D volume.
Okay, perfect. From Ines, 24 patients seems very low for training. Is this only for the tutorial purposes, or if we are using like any transfer learning or any other methods during the tutorial?
Yeah, of course. I mean, 24 images are, um, it's a very small number, right? And of course, this is just for tutorial, and the purpose of using just a very small subset, 10%, is that everyone could run this notebook, right, without I mean, spending any money on GPUs. I mean, of course, if you have access to the GPUs, then go ahead and use the entire data set.
Okay, perfect. Thanks. Another question from Ines: why are skip connections important to the model?
Yeah, that's very important question. And so basically in the encoder part, we have higher resolution features, right? And in the decoder part, because of downsampling, so this fine detail is lost to some extent, right? So the skip connections, they provide this high resolution information directly from the encoder, and this helps the model to better I mean segment, to better localize whatever it is segmenting.
Okay, perfect. Other question from Ines. In this kind of studies, I already face challenges to set hyperparameters for training. Why it is um, why is not usually to show hyperparameter searching in this kind of problems.
I think he's asking about the optimal hyperparameters. Yes, it's challenging. So I answered another question about it. So I mean, I would suggest to start to find a study that uses the similar architecture and similar data set as you are using, and I mean, find a high performing study that has achieved very good results, and start with the hyperparameters of that study. So I think that would be a good starting point. But again, you have to do systematic search. But I should mention here that NN unit is a wonderful framework. So it helps in this regard a lot, right? So it automatically configures for you the best or a very good setting. So I mean, so you don't have to burn a lot of resources to get optimal hyperparameters.
Okay, perfect. Thank you. Similar question. So I guess we'll pass, but just like mention it briefly. I face difficulty when deciding the parameters. When I studied this problem, I didn't fully understand or a set of hyperparameters is chosen, is there any predefined good set of hyperparameters for this kind of network, or it is mainly based on try and errors or a systematic search, for example, to find, like, for example, the best
Yeah, yeah.
duration.
Yeah, I think I just answered this question. So I would suggest, instead of randomly searching for hyperparameters, one should do a systematic search, right? So yeah, it's one of the most challenging problems, right?
Yeah,
It's
yeah, totally.
one of the most challenging part.
Another question from Roja, will I receive a certificate? So yeah, you will receive a certificate. So everyone that wish to get a certificate, just send me an email. You can find, can send me an email to this address, juven.z. I will just type gmail.com and just uh, provide me your name, and I will be sending you the certificate. Okay. Same question from him. Or does a 3D unit architecture capture the spatial context that a 2D unit typically misses?
That's a very good question. So basically, 3D unit uses conv 3D, 3D convolutions. So it processes a volume instead of a 2D slice, right? So it sees the not only just one slice, but it sees across slices. So it is able to capture more spatial context compared to a unit 2D that only looks at one slice at a time.
Okay, perfect. Um, Another question from an anonymous user. Can I use this as my, I think, final year project? I guess, of course, you can. It's a very
Yeah,
great
of course,
material
of
to
course.
start.
Yeah, I would suggest if you want to, do it as your FYP, choose it as your FYP. Choose the recent version of RADS, and I mean, yes, by all means, it's a very good project.
Great. Let's go for the question from Rafik. Is he wanting to flare an MRI modality or sequences? Yeah, used in the
Yes, I've seen that in literature, they have used these terms interchangeably, right? Some call them sequences, and at other places they call it modalities, right? So the thing is that they are so different settings of the scanners, so they sort of highlight different aspects of the brain that help radiologists to you see better see different tumorous regions or parts of tumors. So I
okay,
think that
yeah.
both are used in the literature.
Thank you. Another question from anonymous Andy. In the 3D unit implementation, we use random props, but not in the 2D implementation. Even though we work in 3 space, aren't we only learning local information?
Yeah, that's again a very good question. Yes, you're right. But the thing is, we typically use crops just to save memory, right? But the thing is, we use in this tutorial, we are using just one random crop per patient, but oftentimes the studies use multiple random crops from one patient, right? So it sort of covers, I mean, most of the scan areas, right? So yes, for one scan, you only see a patch, but again, then you have multiple patches, diverse patches from different locations within the scan.
Okay, thank you.
So
Perfect. Another question from Wakas. The green color means the model is biased toward edema, right?
yes, yes, Vikas, it's a good observation. Yes, I mean, because edema is the majority class. I mean, so if we take all four classes, including the background, that definitely background is the majority class. But while evaluation or visualizing, we are ignoring the background. So edema is the majority class of the three tumor classes. So
Mm.
that's why, I mean, I've run the model many times. So often the best result is for, I mean, the edema gets the best results both for unit 2D and unit 3D.
Mm. Thanks. Uh, Question from Mawa. Can we guide the process and define the specific region for uh,
Yes, Marwa asked this, and
for the
I don't know,
segmentation?
I couldn't fully understand the question, but I mean, uh, so as far as I understood her question, so you have a segmentation mask, the ground truth, right? And of course, the ground truth is a way to guide the model to learn to predict specific regions. So uh, I think she has asked another question. So I'm
Yes, yes.
using
Follow-up question.
another. Okay,
Yeah. She
okay.
asked like, I'm using another model for completion, and I want to do segmentation just in the added surfaces. Can I use unit?
Uh, Honestly, I don't understand her question, but if I mean if you are doing segmentation, yes, you can use unit. I mean, are you segmenting natural images, right?
She's probably still listening.
So I
So
mean,
let's see.
yes, yes, for segmentation you can use a unit, right?
Okay, perfect. Yeah. Uh, Question from Andres. Do we have a
Mhm.
timeline on when the BRAS 2026 challenge will be officially released? It's
I
a bit of out
think
of scope.
you guys would better answer this question, you or Diana, if uh,
Yeah, I think you can like look at the MICCAI website challenges once
mhm.
they provide like context on all the challenges. Once it will be added on the website, you will be able to see a link to the results. Okay. Uh, the question from an analyst, Indy, how can I use this as my final year project? Can we get any from that?
Yes, 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 you can definitely use it as an FYP. Consider this notebook or tutorial as a starting point and use a full-fledged data set. I would suggest the most recent version of BraTS or some other data set, right? And yes, use it as your FYP and get good results. I would say if you should participate in a challenge, right? So that would be a great way to demonstrate that you have achieved a good score or a reasonable score on a benchmark, right? I mean, the results, you have got a good score, you are on the leaderboard, right? Uh, Through some external party doing the evaluation for you, right? So it will be more reliable. Your results will be more reliable, right?
No. So a bit of a philosophical question. If skip connection provide information, then why are they called skip? It sometimes feels like something overpassing.
It's I'm sorry, I don't know. Why they are called skip? You know, so basically they pass information from an earlier stage directly to a later stage, right? So they kind of preserve the earlier information and they make sure that the earlier information is not lost uh, while we go very deep in a deep learning architecture.
Okay, perfect. Uh, Question from May. What is the difference between a 2D and a 3D convolutional unit?
Uh, Unit 2D uses 2D convolutions and downsampling and upsampling or transpose convolution is done in a 2D manner, and so it processes 2D slices, right? But a unit 3D processes 3D volumes, right? So unit 3D has the advantage that it processes or it learns from more spatial context or volume, right? So because our tumor is not isolated on a particular slice, so it is spread, it is a volume. The tumor is a volume. It is not a flat 2D thing, right? So unit 3D is, it's more natural for predicting a 3D tumor.
Okay, perfect. Another question from May. Would it be a version like would it be a version with satellite imagery? I think he is asking about if you can use satellite imaging with
That's
this.
a wonderful, that's a great question. I honestly, I don't have any idea about it. But I think if even if you are your project is to uh, do segmentation on satellite images, so I think this tutorial should be beneficial even for you, right? But honestly, I don't know exactly which architectures are more suitable for satellite imagery. So
It's a good start, but yeah, can you
yeah,
look
yes.
literature after? Okay, great. And uh, another question from Wakas, can we call this explainable AI model as it is showing the location of the disease?
Rashid, would you like to answer this question?
Yeah, of course, I will jump in.
Yeah, please
So,
go ahead.
yeah, explainable AI means that we want to understand which part of the model and the weights were involved in the output. Directly using the output is not like explainable by itself. Okay, so because like most of the time, deep learning model are black boxes. So just like having segmentation map, not it's not directly like explainable. Okay, so explainable is when you can like add something like in our case segmentation to be a map that directly tells you which pixels, in our case, were used by the model to provide and construct the output. Okay, so it's different. Yeah, it's just the output without telling like which pixels were used in the process of the decision. Okay. Another question from anonymous Tandy. Where can I find your email for certificate? So pasted in the chat, uven.z@gmail.com. There's a question from Roy. Thank you. I know that my students enjoyed this well-organized video very much. Thank you, Roy, for this comment. And thank
you very much.
May, thank you. So if there is no more question, I would like to end this tutorial, and I would like definitely to thanks Yasar for this great session and this great tutorial.
Yes.
And also would like to, yeah, of course.
Yeah, please go ahead.
Yeah, I would also like to thank Diana for the help for the tutorial. So without her, it would not have been possible.
Yes, I mean, thank you very much to the organizer, Rashid, Diana, Miguel, and Via. It's been a very satisfying experience to be able to contribute back to the RISE-MICCAI community. I mean, it's a wonderful community, RISE-MICCAI, and the whole ecosystem around the RISE-MICCAI, the partner institutions. I mean, like Mohammed bin Zayed University of AI. I mean, these guys have been very supportive. So, for the beginners, I would say if you are passionate about research and passionate about uh, creating an impact. So, I mean, these guys will make sure that you are well supported. So, thank you very much. Thank you very much.
Okay, perfect. So I'll be ending the session. So see you guys and bye bye.
Bye bye.